Okay, it's 7:30 and we're going to get started. Welcome to the January meeting of the Johnson Space Center Astronomical Society. I'm Doug Holland, the president of the JSCAS, and here's our agenda for this evening. First, we're going to have Dr. Aaron Clevenson with your first astronomical instrument. They'll be followed by 2 members' minutes I'll be giving, one about our JSCAS star party at the X-Bar Ranch, and one about narrowband imaging with a 127 millimeter Acromat. Then we'll wrap it up with star party news with David Havlin. If you have questions for our speakers this evening, you can either email questions to the email shown below on this slide, jscslive@gmail.com, or you can enter them as a YouTube chat, and we will get those questions to our speakers. So we're going to do things a little bit different tonight. We had some little bit technical issues, internet problems, and our speaker will be coming to us by way of a phone. So things are going to move along just a little different than normal, but we'll make it through this. So for our main speaker, first I'd like to tell you a little bit about Dr. Clevenson. Dr. Aaron Clevenson is a past president of the North Houston Astronomy Club and past chair of Houston's Astronomy Day. Aaron taught stellar and planetary astronomy at Lone Star College in Montgomery for 16 years, and he wrote the astronomy textbook that they use. He is the observatory director at the Insperity Observatory in Humble. Aaron is an observing program director with the Astronomical League and coordinates their master observer progression, in which he is one of 3 platinum master observers. He remembers his first astronomy experience at 6 years old, when his sister built him a solar observatory from a cardboard refrigerator box with which he saw a partial solar eclipse through a pinhole projection. His interest and goals in astronomy is to see it all. He is here today to share with us one small corner of it all. Now I'm going to switch over to Aaron's slides. Just stand by. Okay, Trevor, can you see Aaron's slides?
They are up.
Okay, Aaron, take it away.
Okay, thanks, Doug and all. Welcome. It's great to be back and sort of with all of you. I know COVID is making things a little bit difficult still, but I'm excited to be here. And I want to talk a little bit tonight about my presentation on your first astronomical instrument. But before I do that, and so I don't forget later, Doug mentioned in that very glowing bio at the beginning about my astronomy textbook. I will give that to anybody who would like a copy. It's electronic, it's free. Just send me an email to aaron@clevenson.org, and I'd be more than happy to send you the link so that you can get a copy of it. Anyway, now down to the topic at hand. So Doug, let's take us on to the next slide, if you would please. And so my question is, what was your first astronomical instrument? And since this is not truly really interactive, we're going to just buffalo through it. But it might have been something like this refractor, or possibly a fairly simple Newtonian reflector. Or maybe it was a bigger Dodsonian telescope. And there's just all kinds of other possibilities. You know, maybe it was one of these cute little tabletop dogs, which are really cool and useful. Another option might be, I forgot what the name of it is, but that's okay. Astrocan, I think is what that one is called. Or perhaps you went for one of the big telescopes, like a large Meade or Celestron, or perhaps even this Takahashi. However, what if I told you that you were all wrong? And I'm sure some of you already caught the punchline ahead of time. But the reality is, on the next slide, your first astronomical instrument was your eyes. And so that's actually what the topic is going to be about tonight. So it was a little misleading on the way in. But we're going to talk about the eye and how it's involved in our doing astronomy and what things affect how well we're able to do astronomy. before giving a talk, talk about why I bothered to even do this talk. So one of the things that came up a long time ago, and I want to apologize up front, anybody who has been to other club meetings may have already seen this, but night vision. Night vision is really important to what we do. We worry about it. We tell people not to use white lights, and all of that is really important. So I want to talk a little bit about night vision and what it is. And then I want to talk about what affects it and what can we control and how long does it take to get it back. Because obviously if you lose your night vision, you're going to be a little bit handicapped for a while, and it's nice to know how long you're going to have to wait possibly. So next. When I look at the overall process of how we get from an object out there in deep space, bringing it all the way into our brain where we can perceive it, then you start with the object. It has to travel through space. Those are obviously all of these different things that affect how well things look when we're looking through the telescope. Space being one of those, the best example is dust clouds. There are dust clouds out there in space that obscure us from seeing the center of the galaxy in normal visual wavelengths. And in reality, there's nothing we can do about that. But then there are some that maybe we can do something about, such as the atmosphere. How can we overcome problems with the atmosphere? Telescopes and the equipment that we're using. Also, our eyes. There are a few things that we can do that will help enhance that. A little bit of topic on the retina, where the object comes in through your eye, goes to the retina, and then, of course, it passes to the optic nerve and to your brain. Those last two we can't do much about either. So we're not going to talk about those either, but we're going to concentrate on those four in the middle. Next. So as I mentioned, there are a few things that are somewhat within our control: the atmosphere of the telescope, the eye, and also the retina. So let's go ahead and pop on to the next slide as well. What can we do about the atmosphere? Well, we don't have a whole lot of control over the weather. However, we can do things that might give us the best possible situation. So obviously, nights of excellent seeing are the best. My experience has been actual excellent seeing is very infrequent in the Houston area. We get really good, but not excellent. But the better and more stable the sky is and the atmosphere is, then the better we're going to be able to see objects out there in space. We want to observe in areas with excellent transparency. And so that means, again, not just the Texas, sadly, because of all the humidity. There's all kinds of things like humidity, dust, smoke, light pollution that affect how good our transparency is, how faint a star can we see. The third one, again, a problem for us here is you want to be higher. And so altitude is very important. But here in Texas, we are where we are, and we got to make the best we can with what we've got. But higher means you have less air, and if you have less air, you have less turbulence and also less obstructions. You'll have less humidity, you'll have fewer clouds, things like that. The next one, which is really useful, and you all know this, but the next one that's really useful is dry. The lower the humidity is, the better the skies will be, and so the better the viewing will be. And then the last one sort of mentioned this earlier, which was you want to get as far away from civilization as you can, because the more people you have, the more lights you have, which means more light pollution, which means more sky glow, and so you want to get away from all that so you get better viewing. So my suggestion is we all need to go down to the mountains of Chile and watch from the southern observatories there, and of course the skies are going to be awesome. Most of us don't have that as an option. Next. So that's atmosphere. Those are the types of things we can do. The next thing that we might be able to control, actually we should have a lot of control over this, is our equipment. So again, guys know most of this because it's pretty basic, but you want to get the best telescope you can afford with the best eyepieces. And the mount is absolutely critical, especially if you're doing imaging. So that kind of goes without saying. Here at the observatory up in Humboldt, the numbers in our mounts are actually more expensive than the telescopes. And they're not little telescopes, big ones. But the mounts are so critical to being able to find objects, and track them steadily. So if you're doing imaging, they stay where they belong as much as possible. Telescope and eyepieces. something briefly here. I was told out at Texas Star Party one summer by the guy in the little spot next to me. He said, "You're not using 2-inch eyepieces." And at the time I was new to astronomy and fairly cheap. And I said, "No, I'm happy with these." And he said, "Try one of these." And he gave me one of his 2-inch eyepieces to look through my telescope. And it was just like being immersed in space. So I understand the value of good telescopes, the value of good eyepieces, and now I truly also understand the value of 2-inch eyepieces over the smaller ones. Not always possible, but a wonderful thing if you can. There's a caveat that goes with the best telescope you can get, and that is it has to be one that you're going to use. So that next dot down is buy the largest telescope you can afford and still use. If you go out and buy the big 16-inch telescope and you're going to be doing observing by yourself, and assuming you want mobile, that's going to be a problem. So you need to evaluate that, and one of the things I've noticed is as I'm getting older, my 10-inch telescope is more than I want to muscle around. So I certainly can relate to this directly. The other thing I want to just pop in here as part of the telescope considerations is you might try light pollution filters. So often, most of my observing, I have not used them, but they are absolutely wonderful, especially if you're dealing with sodium vapor lamps, because sodium has a very specific frequency. It's easy to filter that out. Mercury's worse, and of course, these white LEDs are also much worse to filter out. Because if you're getting rid of much light, you're also getting rid of light from your object. Okay, so that's the telescope. The next topic of where we might be able to do some control is your eyes. And, you know, we are all dealt the eyes that we have, and so there's not a whole lot you can do about that. But there are some things you might be able to do to try to improve your viewing through a telescope.
Aaron, we have a question that's come in. Can you ask a question right now?
Sure thing. I also noticed you're not on the same slide I am.
The question is, what filters have you found that you like the best?
Okay, so we have tried a number of filters. The ones that I originally had bought from Orion, although they're nice filters, they are not as precise, they're not as sharp, so they don't eliminate just the bad stuff. They tend to spread out into the stuff I really want to see as well. And if you will permit me about 6 seconds, I will go over and see if I can tell you the ones we use here at the observatory, because we're really pleased with these. So let me just go get that, and I'll be right back. And you can actually go on to the next slide if you want, because I'm not going to talk about the structure of the eye.
So do you want to be on the
Okay, so sorry about the delay, but I had to go get one of our eyepieces to see what we've got on it.
Okay.
So what we have on all of our equipment at the observatory is an octo-long moon and sky glow filter. And we've been really pleased with what it does as far as filtering out what we don't want, but not losing any more of the light that we do want. Okay. So good question, and thank you. The other thing I'll mention on that, just as a general thing, we also have I have a personal full set of color filters, more than you could ever want to use. And here at the observatory, and again, I'm not talking for doing astrophotography or scientific stuff where we have the scientific filters, but we have the color filters, and color filters are great for pulling out details on objects, depending on what colors you're looking for. But in general, I tend not to use those either, and it's because I'm lazy, I guess is what the answer is. But anyway, let's go back to the eyes. So one of the things I think is very important is protect your eyes. This sounds really silly and kind of, mother henning, but I'm going to say it anyway. Make sure you have them checked regularly. Wear glasses if you need them. Now, there are some things that your telescope can fix for you, such as nearsighted, farsighted. That's not a problem. But if you have astigmatism, that does not work. There are filters that you can, they're not filters, I guess, but extra lenses that you can get that attach to your eyepieces to story that goes with this. I had cataracts. I didn't notice that things were bad, except I noticed I can't see as many stars. And it got to the point where I could only see the brightest stars in the constellations. And I was teaching astronomy at the time, and it's really embarrassing to be pointing out stars that I personally can't see at all. And I must have been close enough, and none of my students called me on it. But my advice there, very short advice, is the minute you know you have cataracts, get rid of them. I was very hesitant, but I'm so glad that I did it. And the other astronomers I've talked to who did it are just amazed at how better things look now. So don't hold back, go for it. And the last one is, again, obvious, but don't be overly tired and try to avoid eye strain. You're sitting there staring through an eyepiece, probably not blinking as much as you should. It does wear and tear on your eyes, not long term, but it affects how good the viewing is. So I've done a few all-nighters, and those are great, but the problem with an all-nighter is eye strain, because you're just doing it hour after hour. I guess another solution to that would be astrophotography. Okay, next. And I got a slide I wasn't expecting. Okay, I guess that's the next one. So your eyes react to light. So now we're getting into the light pollution problems and dark adaptation. Your eyes react to light, and two things happen. The first one is the minute you get exposed to bright light, your pupil constricts. The picture that's on this slide is really scary to me. It's so different. And that's okay. It's protecting your eye. But as soon as the brightness goes away, and now you're back into dark conditions, your pupil will dilate again almost immediately. So I've got the numbers to go here. Constriction is nothing. I mean, it's milliseconds. A tenth of a second to a 20th, or to a fifth of a second. So it's nothing. And the dilation coming back is a few seconds typically. If you're older, it might be up to a few minutes. But that's still nothing, right? If I'm not observing, it'll take me a few minutes just to get used to back at my eyepiece on the telescope. But if we take a look at the next slide, there's another problem. Actually, I want to talk about glare before I went on to talk about the next problem. So when you have glare, this is bright light flashing at you. A couple things happen. So the pupil will dilate fully within 10 seconds of the light being gone. And glare is bad, but glare is not night vision. So if you think about it, you're driving, a headlight's coming at you, you've got glare, it's horrible. But as soon as that car goes by, within a few seconds, 10 seconds, you should have your normal vision back. And that's okay. We can live with that as astronomers because, again, we're talking seconds here. It's not a big deal. Let's go on to the next slide. And it's not doing what I wanted. All right, I'm going to go ahead for a second. Just hold on. All right, we'll get to it. So what about glasses? A few more just background things we want to cover here. So I wear glasses. Mine right now are reading glasses, but I wear glasses. And let's be honest, they do get in the way. So yeah, if you have vision challenges looking through an eyepiece with your glasses, the glasses take care of the challenges, and then the telescope does its thing. So that's convenient, but it doesn't work for all the problems. Let's go on to the next slide. There are also a few things that we do to make it easier to see things, and these are tricks that all astronomers know. The first one is averted vision. For those who don't know what that is think of it in terms of using your peripheral vision, like you do when you're driving. So what you do is if you're going to use your right eye, you look to the right side of the object, not directly at it, and that's wonderful. If you're using your left eye, then you look to the left side of the object. And I'm not going to go back to it because that would be more stress than we need at this point. But if you think about that picture of the eye, there is a blind spot in your eye. And if you use the wrong eye, so if these are not written up here, but if you do the right side with your left eye, it may put that object right in your blind spot. It'll disappear completely. So you want to make sure you're doing it the right way. Right eye, right side, left side. And that works really good. You want to see it with peripheral vision, and the trick is to force yourself not to then look at it, because then then you're back in direct vision again. The other thing we've done, and I don't want other people doing this to my telescope, but I certainly have done it with my own telescope, which is you can jiggle the telescope. And the reason for that is your eyes are designed to see things moving easier than it is to see things that aren't moving. Think of it as you're in the jungle and you want to be able to see that tiger. You don't care what color the tiger is, but you certainly want to see it coming to eat you. So our rods in our eyes are what are much more sensitive, and they get to see things that are moving. Okay, next. So what's the retina look like? So we don't have a whole lot of control over the retina other than protecting ourselves from bright light. But if you take a look at the retina, and I just love this picture, I don't know that that's what it really looks like. It's kind of cute. You have two types of detectors in your eye. You have rods and you have cones. And you do have three different kinds of cones, red, green, and blue. If there are some women on the phone call, there's a good chance that at least one or two of you might actually have quadricolor vision. You may have a fourth cone, just in case anyone's curious. The fourth one is just another color of red. But the one student I had that apparently had quad vision was actually seeing, I don't say she was seeing the color, but she was detecting things outside the visual range that I could not detect. It was kind of impressive. Well, anyway, so you have lots of rods, 120 million of them in an eye, but cones, you only have 6 million. And the thing about the cones, as I've mentioned, is probably on the next slide. In fact, let's just go to the next slide. Boy, that's blurry. At least my copy is blurry. I haven't seen the one on the projection yet. Yes, it's blurry too. That's terrible. So these are the three different cones, red, green, and blue. And the black curve is the rods. So they're a little bit different. But if you look at it, the red's not really peaking in the red. The red cone actually is most sensitive in the yellow. Green's pretty much green. Blue is pretty much blue to violet. But if you take a look at those rods right in the middle at 498 millimeters, that's actually a green-blue color. And so normally what we would say is, although the cones see individual colors, the rods, although we see it as black and white, i.e. white, the rod is actually detecting a color of green. And so green is absolutely a horrible thing because in addition to the dilation, there are chemical changes that go on. And I want to talk about it on this slide, even if it comes up on a future one. So in addition to the dilation, which recovers in seconds to minutes, we also have a chemical change that happens. And in each one of those four types of sensors, it happens when you see light of that particular frequency or nearby. And when that happens, you have a chemical change in the eye. When it does that, it takes time for that chemical to go away. So if you expose yourself, like the red cones, for example, to red light, you're going to lose the ability to see red light for a period of time. The problem with the rods is if you do that to the rods, you lose the ability to see what the rods are supposed to see. And that's a problem because the rods are more sensitive and more valuable to us when we're doing astronomy. So next slide. So when you look at this, you can see the blind spot pretty clearly. There's nothing in the blind spot. And there is also the center of the optic nerve, fovea. And the rods are located around the fovea. That's the red line. The blue line are the cones, which see color, and they're pretty much right in the middle of the eye. So when you're looking at something, let's say you're out foraging, you're looking for a particular plant, what you want is color, because colors clue you in on what that plant might be. And that's direct vision. You're staring right at it. What you see is what you're looking for. Whereas if you think about the rods, they tend to be much more valuable to us in low light conditions because they are about 100 to 1,000 times more sensitive. And you don't want them directly ahead. You want to see the stuff in the peripheral vision because, again, we're looking for that tiger that's getting ready to eat us. Okay, so when you do averted vision, what you're doing is you're looking away from the fovea. And if you're using your left eye, you look to the left. If you're using your right eye, you look to the right. It is inverted in your eye, but let's not worry about that. But the important thing is you want to get it in that large pile of rods that in this graph are off to the left-hand side. If you do that, then it's going to be real sensitive.
Aaron, we have another question for you.
Go for it.
Okay, the question is, what is happening with the eye to get dark adapted? Why does it take so long?
Well, okay, I don't know that I know the exact answer, but I can tell you what I believe to be the answer. Just like after exposing yourself to a bright light in the wrong frequency, it takes 30 to 90 minutes to get rid of that chemical. Well, during the day, to protect the rods in particular, but also the cones when necessary, you have a little bit of a chemical change. It creates these pigments in your eye. I think it's probably the next slide, but you create these pigments in your eye, and you have to wait for those pigments to go away. And I've got a really good graph that shows the timing, but basically the way to think of it is anywhere from 30 to 90 minutes, depending on how much and how bright the light was. So it's the same thing at twilight. You know, twilight is 30 to 90 minutes long. Hey, it takes 30 to 90 minutes for your eyes to adapt. I don't believe that's coincidence. I believe they're reacting to life on Earth. You know, it takes that long for twilight to get dark. And I believe it's the chemical change. Let's try the next slide. I was a little ahead of myself on some of these. Okay, so I mentioned that the rods see black and white. They see white, in other words. But in reality, they're not. They're sensitive to a particular frequency or range of frequencies in the green. But the neat thing about them is they're so much more sensitive. And when we're looking through a telescope, the reason things look black and white a lot of the time is there's not quite enough color photons of the red, green, blue variety to set off the cones. But since these rods are 100 to 1,000 times more sensitive, there is enough light to fire off the rods in the green. So their most sensitive green light, 533 nanometers, which incidentally happens to be very close to a green laser. And the photoreceptor, that's that little sensor in your eye, it has a protein and a pigment. And together they're called rhodopsin. And that's the pigment that's going to cause us problems for night vision. So again, that's rods. Going to the next slide, it'll talk about the cones. So it's a little bit different. This one is called fotoxin. And I think photo, color, okay, fine. Same kind of concept, except as I said, you have 4 of these different cones, but they're not nearly as sensitive. So going on to the next slide. So what happens if we're going to bright light? Well, if a particular cell is sensitive to that kind of light, we get pigment, lots of pigment, so it saturates. In fact, if you want to experience this, find yourself a big white wall that you can use, and what you should do is stare at an object of a particular color, red, green, or blue, and just stare at it maybe 30 seconds, and then when you look at the white wall, you'll see the image of what you were looking at in reverse, because it has filtered out that particular color of light, but the other sensors are still seeing it in the white. So it's kind of an interesting experiment, and yes, it works at home, safe to do. But the problem is, once you expose them, you need some time for those pigments to regenerate the wrong word here, but for them to basically be reabsorbed so that you can actually see in that color again, so that the rods or the cones are not that sensitive anymore. And this is all protective. The iris, the pigment, is to protect it from extra bright light. Anyway, so when this happens and you're waiting for it to regenerate, to get rid of the pigments, your night vision to regenerate, then that's a loss of night vision. So let's go on to the next one. Just a few tidbits here. So as I mentioned, at night we tend to use the rods. In a telescope, we use our rods. They're most sensitive in green light. And the problem is, and by the way, 2 points to anyone who recognizes the album cover to the right. But anyway, the problem is white light is all kinds of light, and it includes green light, so white light is bad. dark side or at a star party, and you've got somebody, it might even be me, complaining that you've got white light, like possibly your cell phone or things like that, it's legitimate, but, you've got to temper that with, is it a public event? Well, of course you're going to have white light. You just got to tolerate it. But it does affect everybody's night vision, and it takes way too long for it to come back. Okay, next one. This is the graph I had mentioned. And if you take a look at it, it's not as fancy as it looks. I don't agree with the fact that on this chart, basically by 40 minutes or 50 minutes, you're supposed to be back to normal, because I do know sometimes it's longer than that. But a couple interesting things. So what I noticed is in 10 minutes, the cones, the color things, are pretty much back to normal. Well, that's great, but I'm not using them at night. I'm not using them through the telescope. So I really have to wait for my rods to come back. And, on here it's implying about 50 minutes, I would say 60 to 90, to fully recover from being exposed to white light, or in this case, green light. But I really like that graph. That graph just tells me a lot of stuff. I don't worry about all the text, but just, what's happening. The cones first and then the rods. Okay, next.
I just want to say we did have 3 winners on the album cover. We had Brandon Riddle, John Harrington, and Justin McCollum. All knew it was Pink Floyd, Dark Side of the Moon.
Yes, I think that is just so appropriate. But yes, well done, y'all. Well done. Of course, I don't know what we're going to give them for the points, but you guys do get some kudos. So what do? Night vision obviously is very important to us. One thing that I would like, while I'm on the topic, let me try this. So when I'm not observing, I have red flashlights. And, yes, I use them for everything. And they don't affect me looking through the telescope, but I have never seen color in things like the Orion Nebula. I know it's there because I've seen pictures, but I've never seen the actual color. And I'm wondering if it's not because, largely it's going to be red, and I'm wondering if I'm not seeing it because I'm sitting there ruining my night vision for red because of my red flashlight. Interesting. But anyway, off topic. So, my advice, get there early so that you can take full advantage of twilight. Let your eyes adjust as the sky adjusts. And then avoid the bright white headlights. Some of these are hard. Car headlights, somebody shows up late, tisk. Computer screens, cell phone screens. What I've discovered on the computers here at the observatory is no matter how much we tweak them, we can't get them pure red. So we actually have red plastic, red plexiglass that we put over all of our computer screens here to get rid of any even trace amounts of not red light. Of course, we're still ruining our red night vision, but we're going to maintain the real serious ones. Cell phone screens are just as bad, even though they're primarily dark. They do have icons that aren't, so they're problems. White flashlights, bad. So you need to have a red flashlight. The reality is it needs to have good red plastic over it. I've heard people say, we can use construction paper. We can use cellophane. We can paint it with a red marker. Well, these are all great ideas, and they certainly improve the situation, but all 3 of those will let white light through. Not much, but you really don't want any. A couple other things, local lighting. What I tell people when they want to know, where can I go observe, like for meteors or something, I tell them to find the darkest place you can where they can't see any ground lighting. Because it's going to sneak in, it's going to creep in, and your eyes are going to see it. The moon is a horrendous source of light pollution. It's one we can't control except by observing at certain times during the month. Unless you're looking at the moon. If you want to look at the moon or even the planets, the moon's not a hindrance. But if you're trying to look at faint stuff, meteors is a really good example. The moon's a horrible hindrance because it causes so much sky glow. And I did mention here, bright objects in the telescope, especially Jupiter, are also a real problem for your night vision. So the answer to those last 2 is if you have to look at them early or at the very end of your observing session. If you can't do that, lunar filters, so officially neutral density filters. And neutral density, standard filter is about 13% pass. So you're only getting 13% of the light, and that's a good thing. What we do here at the observatory is we stack them, 2 moon filters, and now we're down to about 1.5%. And if you're looking at the moon, that's more than enough. Maybe a single would work better for planets. But anyway, okay, next one.
Okay, Aaron, we had one more question.
Go for it.
It says, oh wait, got 2 more questions. Okay, first one is 3 more questions. Okay, why don't they manufacture computer screens specifically for astronomers?
We would have to ask those manufacturers. I have no idea. Actually, in the old days, so I'm a very old computer person, and I remember when computer screens were, I guess they were LED. I don't really know. No, they would have been CRT. But I remember when they were just red on black, and it's a shame we don't have those now because that would have been perfect. Of course, they weren't graphics displays either, but you know. I honestly don't know why they don't do it. Probably too small a market.
Okay, and we have a comment, I think, from Dustin. It says, go far west or deep south Texas to avoid the Texas urban triangle for very dark skies for favorable meteor shower observing.
Absolutely. And as far south and west as you can go is Big Bend, and that's the place to go.
Okay, very good.
Absolutely. What was the third one?
Oh, I combined Justin's 2 into 1. So that's
all right, fair enough.
okay.
Okay, so I'm sitting here at the observatory. We have a spectroscope, and I have data that tells me, and we're looking at that data, which rods and cones are sensitive to what frequency. The thing I do want to point out on this is the brightness. In other words, how far up you go is relative. The top of that graph is 100%. The reality is if you did it without making them relative to each other, that black line would be 100 to 1,000 times taller. So, ignoring that fact, this is just for convenience. But I said, all right, I'm here at the observatory. I have a spectroscope. Let's see if we can test this. So some things I didn't have to test. I mean, I know what my red lasers and green laser are marked. And those are the ones shown on the screen. So 532 is a common one for green lasers. And 650 or 635 are the common nanometer wavelength for red lasers. So what we notice, looking at this graph, is green laser is right in the middle, not quite as bad as it could be, but pretty much right in the middle of where we don't want it to be. So when you use green lasers, which we all do, my recommendation is use them sparingly. If you're working with the public or a class like I've been, then you need them because you need to be able to point objects out and they're invaluable. And let me just mention here a disclaimer, don't point them at an airplane. Okay, moving on. Red lasers are great, but they don't work. You can't see the path of the red light. And you can't really shine them on the object because the object is light years away. So they're not really useful at night. But just for reference, they're over there at 650 and 635. So then I'm sitting here saying, okay, well, so if I'm using my green laser, that's bad. Red lasers don't matter, but I don't usually use them at the observatory or when I'm doing presentations, or I do them for presentations, but not when I'm doing outreach events. So, all right, that's not real meaningful, but let's keep going. So what about red lights? That band up there that says red light is typically where red lights are. And that's a very vague statement, and I'm not sure exactly what red lights we're talking about, but it'll be in that range somewhere. So red lights are not bad. You know, I have red fluorescent bulbs here at the observatory, and they're great, and they're red. And so I think they probably are doing okay, and they're way up there at the red end of the spectrum. So they're really not affecting the rods at all. But let's look at a couple more specific examples in just a minute. Okay, so next, pop us on to the next one. So when I was looking at, well, all right, what do we need to worry about now? The first thing I thought about was bright lights. I've talked to a lot of astronomers who say bright red lights, even red ones, are bad. And I'm starting to wonder, well, how bad are they? Well, first off, they're red, that means the rods can't see them. But they do cause glare. Again, our flashlights that we use here, or the lamps, are very bright. If you look at them, it causes glare. But in a very short period of time, you get your night vision back. Hold on just a second, I need to have a brief cough. Sorry about that. Okay. But we can recover from glare really quickly, so that's not really a problem. So red, 620 to 750 nanometers, and if our red sensitivity drops almost to 0 at 650 nanometers, pure red lights will not affect your night vision. They do cause glare. I have a lot of astronomers who still don't believe me, but when I look at these graphs, there's no way that those red lights can ruin your rod night vision. Anyway, let's go on to the next one. Well, what about some of the things that we use to try to protect ourselves from red light? So we use something called ruby lith. That's the plastic that we use here and at the college as well. And you can buy it. If you're somewhere big like an observatory, it's worth buying by the roll because the sheets are expensive. The roll is ridiculously expensive, but the roll is like 100 sheets long. I mean, it's just huge. Anyway, so we put a piece of ruby lith in front of a white light. And the nice thing is it's a gel coating. It's really good, and it really does block out all the light except the frequencies that it's sensitive to. So this graph, that little red line, shows you where we were picking it up in the spectrograph. So yeah, there's a little bit down there in the green, but it's really, really low level. And it doesn't start getting bright until you're up above 600. So my statement to this is I think the ruby lith would be pretty good. You can put that on. It'll block out almost all the light, and the red light it looks through is well above where you're going to be sensitive. There's a little bit of overlap, but very little overlap. All right, next one, please. What about red LEDs? And a lot of us have red flashlights that we bought that are red LEDs, which is wonderful. And the nice thing about red LEDs is they're very narrow-banded. I mean, they're wonderful, nice narrow frequency. So if you take a look at this chart, this was the red LEDs we were testing that day. They're well into the red. They're actually better than the ruby lith in that regard because they are so precise. And so red LEDs, LED flashlights, awesome, good thing to do. All right, let's take a look at the next one then.
Okay, Aaron, there's a question on that.
Okay.
So you say you're testing these LEDs in ruby lith. Do you actually have a spectrometer at your observatory?
Yes, we do. We did spectral analysis on them and then superimpose that on that graph. You know, the graph with the rods and cones on it is our standard background graph. But our spectral analysis tells us what wavelength it starts, peaks, and ends at. You know, so we get lots of really good data. Yeah, I'll give kudos to the guy who did it. Some of you know him, Bruce Pollard, the current president of Northeastern Astronomy Club, is the one who typically runs our spectroscope for us.
Okay. This question, can you tell us what spectrometer that you use?
So yes, I don't know how practical this is for the common person, because again, remember we're an observatory, but we have an L high res from, and of course I can't remember the name of the company. They're in France.
Right. Okay. Great. Thank you.
Look up LHIRE, probably F for resolution. If you look that up on the internet, it'll tell you who it is. I just can't remember off the top of my head. Not cheap at all. What I like about it is it came with 3 different gradings. The lowest one is, 600 lines per millimeter or something ridiculous. And the highest resolution one is 2,400 lines per millimeter. And we have 3, so you can put in the one that best suits whatever you're trying to accomplish with a spectroscope. You can also get much less expensive options, even as simple as filters that you put on the end of your eyepiece, that when you're looking at a star, it'll show you a spectrum that fits in the eyepiece, and you can make out the dark lines. It's just not, high resolution, obviously. But, yeah, so there's lots of options out there. I love the one we've got, and certainly if you have the money for it, it's the way to go. It's probably one of the better amateur ones. Any other questions?
Not this time.
Okay. So let's go on to the next one. Again, I'm repeating myself a little, but repetition is good. So we've tried the red computer screen thing. I did not try it with the spectroscope just because I could see the white. If I can see it, then I know the spectroscope will pick it up. The construction paper, that's such a bad idea. You don't need to make it that dim, first off, and second off, it does not filter out the white. I had an astronomer at the college that says, I'm going to cover my flashlight with a red magic marker. That doesn't work either. And I mentioned cheap cellophane as well. Let's just go on to the next one. I thought I ought to put a note in about imaging. So far we've largely just been talking about the eyes. But, a lot of us are imagers, so it's important. And often we are imaging, if not in color, then we are using color filters to get color. And part of what we collect is red. So you need to be sensitive when you're working around people who are doing imaging or if you're doing imaging, because even red lights and red computer screens can cause a problem. So be courteous and considerate and all that good stuff. And then this last one is what I mentioned about I've never seen it, and I've never gotten around to that. I want to do it out in somewhere where it's really dark. So I'm going to go out to Big Bend. I'm not going to use my red flashlight, and I'm going to do it during the winter because, first off, it's cooler, but also because I want to look at Orion and see if I can see red. I know other people have. I know no reason why I shouldn't be able to do it, so I would like to go out and try it. But I know I need not to use my red lights. Okay, and that is it. So if you go on to the next one, I will take any additional questions we might have.
Okay, one additional question is on early in the presentation you mentioned about cataract surgery. When you had cataract surgery, were you able to focus as well afterwards as before?
Okay, so since somebody brought it up, and I assume I'm ahead of time because I usually talk rather quickly, I'm going to elaborate a little. So I already told you the story of why I decided I needed it. And so you are all astronomers. You need to know these things because of considerations. Now, you may come to different decisions than I did, but you need to know about them anyway. So to answer just the question first, they did one eye at a time about 2 weeks apart. And by the time they got me back to recovery from surgery, I was awake and I could see probably 20, 30 or better. They didn't measure it, so I don't really know, but I could tell, hey, things are sharp. That eye can see stuff. I mean, it's just amazing. And by the following day, that eye was measured at 20/25. 2 weeks later, it was measured at 20/15. And that eye, which was my left eye, is still at 20/15. The right eye, not quite as good. The experience in the recovery room was roughly the same. It sees 20/20. But it was instantaneous. I mean, I could immediately see better. And, it takes a little time for some swelling to get out and things like that to get to whatever your standard vision is going to be at from that point on. But it was a wonderful experience. I recommend it highly. I do have one other recommendation, just in case any of you are thinking about it. They can do it two ways. They can do it with a laser, or they can do it with a scalpel. And I have the greatest respect for my eye doctor, and I think he's probably one of the best, and that's what you want to think about your eye doctor. But I saw the option of using the laser, and I saw the laser worked because I lived through it, and I've come to the conclusion that a trained monkey could run that laser. Whereas a scalpel, that's technical dexterity by a person, and that worries me. So my recommendation is go with a laser. The reasons are, first off, it makes a little 2 millimeter long incision, and they do everything through that tiny little hole, whereas the scalpel is a bit bigger than that. Recovery, I would say within 2 days, my eye had healed because the hole was so small, and it takes possibly a couple weeks if they're doing it with a scalpel. So for my money, I said, I don't care if my insurance is going to pay for the upgrade to the laser or not, we're doing laser. you're in there being lasered, they can fix nearsighted, farsighted. They can fix astigmatism. The only outcome was I do need reading glasses now to read, which is a little bit of a pain. I've always worn glasses, so it doesn't bother me. But it means if I want to look at something close, I have to put them on, like my speedometer, and I have to take them off if I want to see the road. So the other two things I just wanted to mention, because I said I was going to mention them, was one of them is they tried to talk me into getting one eye set for near vision and one eye set for far vision. And I'm convinced that would have worked perfectly fine, except I do astronomy that sometimes is binocular vision based. I have binocular telescopes, binocular viewers, binoculars themselves. I want my eyes to behave the same way. I know they're not going to be exactly the same, but they got to behave the same way. So beware of that. They want to talk to you into that and decide if that's right for you and your life and what you do in astronomy. If all you're doing is looking at images, or if all you're doing is looking through one eye through a telescope, that might not be a problem. But for me and what I did, that could have been a serious problem. The other thing was he said, we have these really neat lenses. They're called Snell lenses. It's spelled Fresnel, in case anybody is not up to what I'm talking about, but it's what they put in lighthouses. And it will do great things to enhance your daytime vision. The problem is, at night, looking through a telescope at little dots of light, you'll get diffraction rings. And I said, no, we're not doing that either. And they tried to talk me into that one as well. I just said, no. Just normal lenses. And I have been so excited about my eyes since they did this. I now can see all the faint stars. Things are back the way they should be. The other thing I noticed was, and I didn't notice this going in, but I noticed around my house, I have crown molding, and my crown molding is white. And I noticed, all right, the house is 30 years old, and I said, it's starting to yellow, maybe we need to repaint it. And as soon as I got the cataract removed, it was bright white again. So there was a color change, I just didn't notice it. Any other questions?
Not this time. Let me put Trevor real quick. Trevor, is there any that came in on the email? I'm not hearing from Trevor. Okay, I'm going to assume that there were no more questions at this time.
Okay, well, you all know how to reach me. You know, we've been friends for a long time, so just send me an email. If you do have any, I'd be more than happy to answer them. I'm going to hang around in the background here, and we'll pop back in a little bit later in the meeting.
Okay, very good.
All right, thank you. Good talking to y'all.
Okay, I'm switching back to the other presentation. Okay. So Trevor, let me know
You're
when you
up.
can see it. What?
You're up.
Okay, very good. All right, so thank you very much again, Aaron, for that very interesting presentation. He surprised me that it was about the eye. I didn't expect that, but that was very interesting, very practical. Okay, next up we have 2 members' minutes by me. And let's see, the first one is about our JSCAS Star Party at the X-Bar Ranch. So at the end of March and early April, we are going to do an extended star party. We're going to start out at the X-Bar Ranch, and we're going to go there for the March 26th through the 30th. And then we're going to move from there to Fort McCavitt from March 31st to April 2nd. And this is a reminder of the presentation I gave last month, but we're reminding everybody to get signed up for this. The X-Bar Ranch is about 58 miles west of Fort McCavitt, so they're pretty close to each other. And this ranch is actually used all year long by astronomers. The guy that is our point of contact there, Stan Metter, advised us that around the new moon each month, this place gets booked up. So it's a real good idea for everybody to go ahead and get your reservations if you'd like to go, because it will probably be booked up pretty soon. It's only a couple months from now. Bortle 2 skies there, both Fort McCavett and X-Bar, both Bortle 2. So Bortle 1 is the theoretically darkest skies there can be. So Bortle 2 is pretty good. Not as good as Big Bend, no, but it is one number just less than that. At the X-Bar Ranch, they have cabins and they have RV sites available. I think the RV sites are $30 a night and the cabins are $100 to $150 a night. And once you rent a cabin, you can use the lodge and the kitchen, the dining room, and all that will be available to us. So it's going to be really good. It's really a nice place. You got to bring your own food. They do supply water, and they'll run electricity out onto the observing field for all of us. So that's going to be good. And make your reservations. It's going to be a blast. We're going to have fun. The website to go make your reservation are www.xbarranch.com, as it's shown here on this slide. And we're calling this the 2022, the year of astronomy for the JSCAS. I hope you can participate in this. Okay, my second members minute is narrowband imaging with 127 millimeter achromat. I gave a presentation on this a few years ago, but I'm going to show you another example of this that I finished last week, another image. But just to review what the telescope is, it's a 127 millimeter aperture f9.4 objective lens, which is 1200 millimeter focal length. It's an achromat, and they are available on and off from Surplus Shed, and Surplus Shed has other sizes of objective lenses you can make telescopes out of. Then also, let's see, this the tube is a Hastings irrigation pipe with flocking on the inside. The flocking is a big deal because you can see how shiny this pipe would have been otherwise without flocking paper. I got the flocking paper from Edmund Optics, and it really made it a lot better. And these tube rings here, I got these from Ageno Astro Products. They're the black doodads that hold the tube onto the telescope mount. The sunshade up here is just a mailing tube that's been spray painted black, Surplus Shed focuser. So it's a low cost refractor option. Now there are some limitations though. When you go with an achromat, which is fairly low cost way of making a telescope, this telescope costs just a little over $200 for me to put together. I did get a really good deal on the objective lens, but they are still fairly inexpensive. People would have told you in the past, I don't think this is true anymore, but it used to say that for a good refractor is basically about $1,000 per inch. So there's a 5-inch telescope. This would have cost me $5,000 for a really good, or more for a really good refractor, and this one was just a few $100s. But it's not a wonderful telescope. I'm not telling you that, but you can do some very interesting things with it. One of the issues with an achromat is chromatic aberration, which means that the lens cannot focus colors at the same focal plane. Like in this example here, this is blue is focusing here, and green's focusing here, and red's focusing here. So the results of that is you have images like this picture of this horse down here, and you have colors hanging out on the edges of the objects in your image. But there's a way around that. If you're doing imaging like what I'm doing, you can actually do narrowband imaging, and instead of having wide ranges of colors or wavelengths, you can have very narrow ranges of colors, and that actually gets around this chromatic aberration issue. So in this case, I'm going to show you an example of a hydrogen, which is a very narrow band, very small range of colors, and then I'm going to use an oxygen in a very small range of colors too, to get around this problem with chromatic aberration. Another issue with this particular implementation is the images I'm going to show you were taken at f6.68. This was done by putting a focal reducer. Surplus Shed also has focal reducers, and I can reduce the focal length from 1200 millimeters down to 848 millimeters. That gives me a wider field of view. And that's all good. It makes the telescope gather light faster since it's lower F number, and it gives you a wider field of view. But the downside on this implementation is it has vignetting. So these dark areas in the corner here in this flat image is vignetting. Now I think though, probably what I could have done to take care of this problem, or at least improve it quite a bit, is if I put the focuser farther away from the objective lens. So here's the focuser here, here's the telescope tube. If I make telescope tube longer and put the focuser farther out here, I would have had a shorter distance of these narrower tubes here. I believe what it is, these narrower tubes have too long of a distance, and they're cutting off the light in the corners. So that's one little thing I could have done better on this design and probably improve that vignetting. So here's the picture. First one I'm going to show you. This is the NGC 2264 area, and in a minute I'll tell you what these different celestial objects are in this image. But right now the point is that this is a hydrogen image, so very narrow band, and even with an achromat, a low-cost achromat lens, you can produce a fairly nice image. The detail here is nice. There's not a whole lot of other aberrations, and pretty good resolution, and it's a fairly good image. Now back on the subject of the vignetting, so even though I have vignetting in the corners, you can always crop out the middle, which is what I did here. I cropped out the middle to avoid the vignetted corners. Pretty decent looking image, I think, but accomplished by doing narrow band with an achromat. Here's a color image where I combine the hydrogen and I map that to red, and I map the oxygen to green and blue to make a color image. So this is called the HOO palette, which is hydrogen, oxygen, oxygen instead of red, green, and blue. And again, using narrow band, you don't see colors hanging out on the sides or anything like that. It overcomes the chromatic aberration issue. And as you can see, it's a pretty decent image. So my point of this whole thing is, even with a low-cost homemade refractor, if you use this for doing narrowband imaging, you can actually produce fairly nice images with it. And I know there's some other members of our club that are working with these surplus shed objective lenses and some others and trying to build their own telescopes too. So this is kind of results you can expect. Oh, and also, by the way, that hydrogen was 31 10-minute exposures and oxygen is 22 12-minute exposures. Now, as for what's in this area here, this is the NGC 2264 area. This is the Christmas tree cluster. I'll try to help you see the Christmas tree. Imagine this as being the trunk of the tree, and say this is the star of the Christmas tree, and you can kind of see a triangular shape to it here. And you can imagine these stars going across here, maybe being the lights on the Christmas tree. So the Christmas tree is kind of laying over its side to the right. These are the lights, kind of a triangular shape for a Christmas tree. That's the Christmas tree cluster. It also has the Cone Nebula over here. It's a very nice area. And then there's the Fox-Fur Nebula over here. If you use your imagination, you can kind of see a fox's head here, and then this fur on the back here is called the Fox-Fur Nebula. Over on the right-hand side, you see this very dark area. This is a dark nebula. It's LDN 1613. It's up here and down here. Both are one single area, dark nebula. There's actually a very small background galaxy there that I can't see in this image, but it's actually located right there if you could see it. So that is it on that. If you'd like to see that image, or if you'd like to see other images I've taken and other astronomy related topics, you can go to my webpage, www.holland-observatory.net. And that's about it. So next up, we have David Haviland with Star Party News.
You're up, David.
All right. Thanks, folks. Star Party News for January 2022. We've had nothing in December since the last meeting, but as you can see, we can start getting things populated out. As early as March 4th, we have the first of 5 Hack Winery events, 6 to 10 p.m. That's going to be a Friday night. There's a 5% moon that's going to be way off in the western sky, but given that we're still inside daylight savings, it should be a good DSO night. We should be able to get some life out of M42, among other things, for the crowds. Recently, as of yesterday, we've got March 12th, Saturday. South Shore Harbor Magnolia Creek Golf Course has been poking at Doug and myself for a couple of Star Party events. We finally were able to settle on a date. It's under discussion, but it too is slated for 6 to 10. But we have to discuss that because right now he's only talking about 30 people, and that's an awful long time just for 30 people. He may be able to call out more. We may adjust the hours, but at least we can put a placeholder in that spot. Moon will be 71%, and it's going to transit at 8:30, so it's going to be up a good part of the night. And as
David?
Doug mentioned, yeah,
Is that an event at each course, or because those are two separate courses?
that's how the guy described it. And
Okay,
I don't
so
know that. To my knowledge, it's going to be at the Magnolia Creek.
okay,
Okay, March 26th, as Doug discussed, March 26th through March 30th is at X Bar, and Tuesday from the 30th, I'm sorry, Thursday from the 31st through April 3rd. Sunday is at Fort McCavity. I already discussed that one, so I'll let that one go. We've got 5 more dates to pick out for Hack Winery. We'll just take them as we go. Oddly, up until about September, most of the decent nights as far as the moon and trying to keep the moon in play inside daylight savings is going to be the first 2 weekends of the month. And we'll just play, as I said, we'll just play it by ear and go from there. Hello, computer. I got to update this thing in 2022 at some point. It should let me advance. Last time. Sorry, folks. I'm just getting the spinning wheel of death right now on a slow computer. There we go. Oops. Oh, we just crashed. Let me pull it back up. Let's go back out and start this again. All right. The CDC hopes they're starting to relax things, but now we know Omicron has been around. We'll help get back to normal. We have to abide by the rules and regulations of the venues that they ask for outreach. I now have personal experience. I was vaxxed and boosted all 3 times with Pfizer, but yours truly came down positive as of January 3rd, and I am completely convinced, as my day job is also immunology, that those 3 vaccines kept me out of the hospital. The data is very clear on that, at least through Methodist. 2,700 breakthrough infections through employees, only 1 needed hospitalization. So the vaccines may not be perfect, but they're working. Now, I've moved this up from the back end because I've got a digression to go through. So this would normally be my last talk. So it's really not that's all, folks, but that's all for the Star Party report. It's Sir Haley looking at a cabinet of his cleansers saying, where's that blasted cleaning power? Haley searching for his comet. I can hear the groans from here. All right, let's take a big walk down memory lane. For some time, I have been in possession of the mirrors that at one time were in the Krauss telescope. The Krauss telescope has a very long history with JSCAS. It was there before many of us right now were involved with the club. I became a member in 1999, and this was all the way back in June 3rd of 95 when Chuck Shaw, who was a flight director, last flight mission he worked on was the last Hubble servicing scope, helped set up the Krauss scope at Armand Bayou Nature Center. Armand Bayou Nature Center and JSCAS have quite a history. And what happened is I've ended up with the mirror, and I ended up with the logbook. And this is a snippet from the logbook. I've scanned the logbook, and it's a very interesting read through the club's history. And I'm going to be putting it up on the website. As an abstract, the story of the Krauss telescope starts out great, but then it fell on hard times, and we're happy to say that the story continues and will have a happy ending. As I said, the first entry was June 3rd, 1995, by none other than Chuck Shaw, bragging about having trained 11 people for training. The main players at the time were a gentleman named Brian Zemba and Chuck Shaw, from what I can tell. There were others. If I miss you and I don't describe you and you're on this call, by all means, ping me by email and let me know. So there's part of this story that I have absolutely nailed down, and there's part of it that is an educated guess. So I may not get all the names straight, and if I do, it's surely an error of omission. July 15th, the observatory was open and dedicated. There were 60 and plus in attendance, even though there was a light rain. Dennis Webb, a gentleman named George Gigeman, and Jan Kraus spoke. Bob Taylor and Randy Moore had come out to work on the scope. Past President Ed Malowitz was apparently trained as a TO as well. Other operators included a gentleman named Jerry P. I do not have a last name. Becky Ramatowski and Sue and Mark DeCellis. In '98, astronaut Chris Hatfield came out and viewed the moon, among other objects. Longtime past member and Fort McCavitt attendant Kurt Mars noted over the years as having come out to clean it a few times. It needed cleaning because the Kraus scope is in a swamp, a deep swamp. There are a few notations of mud dauber nests needing to be cleaned out, and you'll see that in a bit. The last entry, however, was 21 February 2004 by Brian Zemba, who signed off saying, good luck. He was heading to Colorado. This isn't to say that Randy Moore, who took over from Brian Zemba, didn't have a log, nor did Ron Rosenwald, who didn't have a log, but only the log from Brian Zemba is the one that made it to me with all the hardware. History at this point starts getting foggy and is not as solid as the written log. Randy Moore became the main telescope operator, then at some point he opted to step away, and Ron Rosenwald stepped up to operate the scope. I think I had just taken over as president when Ron Rosenwald did that. Ron went out anytime there was a call, but calls stopped coming from what I can tell around late 2006 to 2007. He had since moved to Sugar Land. The scope went largely unused for about a year before Hurricane Ike hit, which was June 13th, 2008. There were no calls for use after that, so sadly, the scope sat unused through the rest of 2008 and 2009. This is actually a plaque that is on the scope, and it's a testament to the level of corrosion and degradation, unfortunately, suffered by the scope. Fortunately, translated by, I just dropped his name, Jeff Stone. The original script had Gary L. Kraus telescope. It's a 12.5-inch f7. That's a long one. The tube on this is about 85 inches, 14 inches in diameter, some 85 inches long. Built by Cary Kraus in '67 and placed there in 1995 by the Johnson Space Center Astronomical Society. Here's some pictures of it taken by Chris Randall and John Erickson on August 23rd, 2010. That date will circle back to us. There's a picture of the scope with the mount. This top shed slid off on the rail on the tracks. It was 120 volt powered. It's not those little 12 volt DC stepper motors or anything. It was a heavy beast. Mud daubers were periodically cleaned. The log makes mentions of the tube being cleaned out. It was not uncommon to have these in the scope every time you opened it up. So the story goes on and continues. Sometime late in 2009, 2010, I was still president, and roughly a year later, Armin Bayou asked JSCAS about resumption of outreach activities. We were delighted, but needed also to assess the scope's operation and line up operators. Things were rolling along, and then I got an actual physical phone call from Armin Bayou Nature Center around late June of 2010. They had had a quick change of plans and were repurposing the land. They now wanted us to remove the scope, as bulldozers are going to remove the cement base in about 30 days. Ouch. As I understand it, Bob Taylor, John Erickson, and Chris Randall removed the scope, although I only have pictures of John Erickson and Chris Randall. It had not weathered well at all and was largely inoperable. Chris told me that the 120 volt systems wiring had decayed. The tube was heavy cast aluminum. It was unsalvageable and weighed a proverbial ton. Tracy also would have liked to have flipped it over to a Dob, except the fact that it's an F7 and the tube could not be stored in the Dob shed next to the research dome. The mount was badly corroded and fused and was otherwise non-salvageable. The environment had been pretty brutal to it. We have no idea, nor any record, if any minor flooding had occurred or if water had possibly come up to the gears, but not to the scope itself. Chris kept the mirrors, was going to try to fashion it into the Dob for the LPI, who actually also turned out not to be interested in the scope of that size. Chris needed to start downsizing, and the mirrors ended up under my bed about 3 years ago, where the vacuum cleaner and my toes would occasionally remind me of the mirror's presence. I used the mirror in the December 20th presentation and showed it being cleaned. There it is, all loaded into Chris's truck before he was taking it home. You can actually see some of the unfortunate corrosion on the mount. Here's part of the presentation I did in December of 2020, where we talked about cleaning and tuning up a Dob. I also used this mirror as an example. You can see Krauss right here on the side of the mirror. And no, this is not scratching. This is actually the mirror at that time when I cleaned it is in exceptional condition. Yes, you can see a flashlight through it, but there's one little modest scratch on it. But my personal viewpoint is the mirror has got some exceptional life to it. So on the bright side of history, I noted an email by Aaron Clevenson that was sent to NHAC, and this is my final slide, asking for mirrors for an amateur telescope making project that he was driving at NHAC and Insperity. So I checked with Doug Holland and Chris Wells for their authorization to donate the Krauss mirror to this cause, with the hope that yet again the mirror would see the night sky and be used for viewing by the public, which was the Krauss family's intent. Understand that we had no plans to do anything with it at our end. Until we get some donations, Harvey had ended our telescope loaner program. We reached an agreement, and the remaining equipment, that being the primary, secondary spline, and the focuser, were transferred to Aaron on July 18th, 2021, as a side trip as I was on my way up to Intercontinental to pick up Connie from a girls' weekend out trip. At this point, I'd like to get Aaron involved here. And I would like to, probably one of the few times, speak for the club, Aaron, and say that when you start working with this, if you start taking pictures and show us a progression of how things are going with the mirror and what you guys are doing with it, even if it's only for 10 minutes, the club would love to hear it. So with that, Aaron, if you'd like to chime in and say anything, by all means, please feel free.
So, Aaron, did you hear David's question?
Yes, I did. And let me just go ahead and try to pick up the story here. First off, let me just say that on behalf of NHAC and the observatory, we are honored and quite humbled to take possession of this mirror, noting its long and I think fairly distinguished history. That's a very exciting path, and I'm hopeful that we will be able to move on into the future and do more great things with it. So let me tell you where we are. So we have it. We've looked at the primary mirror, and we agree with Dave's assessment that it's in pretty good shape, considering how old it is, and we think that it will make a wonderful mirror. Also, as David mentioned, it has a very long focal length. And that is an issue. We understand that that's an issue, and we think we have a solution. So what our intention is to take that 12.5-inch mirror, and we're going to turn it into a Dobsonian telescope, but we're going to do it with an off-axis secondary mirror. So the light will come in, the mirror will be slightly tilted, so it'll send the reflection off outside of its own tube. And that reflection will hit a secondary mirror, which will then go to actually a tertiary mirror, which is more of a diagonal, where it will come out, and then you'll be able to look through the side like you would any other telescope or most other telescopes. So that's the plan. That was a very big, ambitious plan. And so we decided before we were going to do that, we were going to build an optical workbench. And I'm very happy to say we have the optical workbench. It's all constructed. We have not yet put the mirror into it and saw exactly what we can do with it. slightly folding it. So if you think about a catadioptric telescope, typical Schmidt Cassegrain or something like that, we're going to try to do similar types of things, except we're going to also move it off axis so that you get the full benefit of having a 12.5-inch aperture. No central obstructions. So again, we have the workbench all set. There are a few adjustments that have to be made to the holder for the primary mirror. And so that's what's holding us back now. And of course, we've had holidays and everything else that just slowed us down as well. But yes, this I'm expecting will be an absolutely awesome piece of equipment once it's put together in this configuration. We expect it will be much shorter. And we have not done the design for the telescope yet because we want to run it on the workbench to see exactly where the different components need to go. So that's kind of where we're at. Here we are at roughly year 25. Let's see what we can do with it now.
Great. Okay, well, thank you very much for that update. David, do you have any other comments about that?
I'm good. I'm done.
All right, very good. Okay, so I will assume we're moving on. Thank you very much, both David and Aaron. And let's see. Okay, so that is it on our meeting tonight. Thank you very much for attending. Our next meeting will be on February 11th. And believe it or not, we're going to have Steve Flanders from the Palomar Observatory. That's where the Hale Telescope is located in California. Is going to come and speak to us about building the Palomar Observatory 1928 to 1949. So that's going to be a really great meeting, and I hope all of you can attend. Thank you very much for attending this evening.